Today, this is for class 12. The chapter is moving charges and magnetism. I am going to deal with that is your topic is magnetic force. Topic is magnetic force. Magnetic force on current carrying conductor. Magnetic force on a current carrying conductor. Magnetic force on a current carrying conductor. Moving charges and magnetism. This is the chapter. Magnetic force on a current carrying conductor. That means here this is a conductor and current I is flowing through it, and it is placed in a magnetic field. It is placed in a magnetic field. It is placed in a magnetic field. Let the length of the conductor be L. Length of the conductor be L, and your cross-sectional area be A. It is placed in a magnetic field. When a current carrying conductor is placed in a magnetic field, then the force exerted by this magnetic field on the conductor, we have to find out the force exerted by this magnetic field on the conductor. So here the length of the conductor, it is L, and A, it is the cross-sectional area, and this number of N is equal to number of charges per unit volume. Per unit volume. This is the number of charges per unit volume. So here you see that we know the Lorentz force, that is F is equal to Q V cross B. V cross B. Remember that such type of formula is very important for to solve problems, because here F, V and B, it creates a three-dimensional figure. What is the problem here is that it creates a three-dimensional figure, and the direction, that is, you have to follow the right hand thumb rule, that is the directions of the force, direction of the force, all these factors comes here, and this V cross B, that means V cross B, they must be in the same plane, and F, it will be perpendicular to the plane containing V and B, because as per your cross product rule. And at the same time, what is that means it goes, this problem goes to three-dimensional. So solving three-dimensional figure, you have to take many cautions. So here, what is your Q? Your Q, that means here it is charge. What is your charge in this rod, in this conductor? Your charge is per unit volume. That means for this LA, number of charges L and LA. This is the number of charge into Q. This is the total charge here. So this is the total charge here, and here, since the charge is moving, it is we have to take, that is drift velocity cross B vector. Drift velocity cross B vector. Now here we see that here again, this you must know that this F, this you know that your N, L, A, N, L, A, I'm sorry, no, N, L, A, not L, N, A, you know that N, A, Q, V, B. We are taking the magnitude. You know that N, A, Q, V, B. Then here comes your L cross B vector. So here you know that your F NAQVB, this is the current here. So I L, this is L cross B, L cross B. Now, since current is your scalar quantity, so F is equal to I L cross B vector, L cross B vector. So this is the force exerted by the magnetic field on the current carrying conductor. So this is the force exerted by the magnetic field on the current carrying conductor. So this is a simple theory. Now I am going to tell you some of the basics and deal with some of the problems here. The problems it is given in your book. I am going to deal with the problems which are given in your book. And these problems, these are very important problems. These are very simple problems, yet they are very important. So the first example here, it is given here. The first example, you see this. Here the example, it is taken from your textbook. A straight wire of mass 200 gram and length 1.5 meter carries a current of 2 amperes. It is suspended in mid-air by a uniform horizontal magnetic field, by a uniform horizontal magnetic field B. What is the magnitude of the magnitude of the magnetic field? What is the magnitude of the magnetic field? This is the question. It is from your textbook. A straight wire of mass 200 gram and length 1.5 meter carries a current 2 amperes. It is suspended in mid-air by a uniform horizontal magnetic field. B. What is the magnitude of the magnetic field? It is suspended in mid-air. The question is given. It is suspended in mid-air by a uniform horizontal magnetic field. B. Horizontal magnetic field. B. Let me remove this. It is suspended in a mid-air by a uniform horizontal magnetic field. The sense is something else. A straight wire of mass 200 gram and length 1.5 meter carries a current of 2 ampere. It is suspended in mid-air. Let us take this, because here it is the question. It is suspended in mid-air by a uniform horizontal magnetic field. By a uniform horizontal magnetic field. What is the magnitude of the magnetic field? So here, by a uniform horizontal magnetic field, it means little bit clumsy. So I have made it as simple. That is a straight wire of mass 200 gram and length 1.5 meter carries a current of 2 ampere. It is suspended in midair. What is the magnitude of the magnetic field? When it is suspended in midair, this is a horizontal wire, and it is mass 200 grams, so its weight will be at the center of gravity. This is the mass will be mg. It is suspended in the midair, and a current flowing through it is I current is flowing through is 2 ampere. Now, what is the magnitude of this magnetic field? So see, it is suspended in the midair like this, or it is suspended in the midair, and the weight is acting downward. So this current carrying rod, it is placed in a magnetic field. So here you see, to balance this weight, the force exerted by the magnetic field must be upward. The force exerted by this magnetic field must be upward. Then only this will be balanced. So here, that means the force exerted by the magnetic field must be upward. That is, this force is equal to I L cross B. This will be I L cross B. Now here you see that, so to the force to be in the upward direction, so here this is your conductor. So your magnetic field, so here your magnetic field must be, this is here, so your magnetic field must be like this, moving like this, Oh, so your magnetic field is horizontal. Yes, you can take this, your magnetic field is horizontal. Midair by, it is correct, by a uniform magnetic field. Now it is all clear here. You see that. So here you see that this is your conductor, and your magnetic field must be in this direction, horizontally in this direction. So now in this direction, then your L cross B, this is L and this is your B. So L cross B, here you see, this is your L, this is your L, and this is your B. This is your L and this is your B. So L, here this is your L, this is your L, and this is your B. So this is L cross B, L cross B. One unit. Horizontal. So this is your conductor, and here this is your magnetic field, this is your magnetic field. So L cross B, L, this is your L, and this is your magnetic field. So L cross B. Here you see magnetic field, and this is your, so L length, and B, L to B. You are moving from L to B. L to B. You take like this. This will be very easy. This is your L, and here this is your magnetic field. So it is in the horizontal plane. It is in the horizon, L to B. See here, L to B. Your L to B, L cross B. That means you are opening the screw. L to B. Here you see you are opening the screw. That means the force will be in the upward direction. So that means your magnetic field will be into the plane of the paper. So your magnetic field will be into the plane of the paper. Your magnetic field will be into the plane of the paper. into the plane of the paper. So your magnetic field will be horizontal. Now everything is clear here. So this is a simple question, but what is the main factor here is that the direction. What must be the direction of the magnetic field so that the force will be exerted in the upward direction to balance the weight. So here you see the current carrying conductor, this is the current carrying, and the magnetic field is in the horizontal direction, So it is in this plane. So here L, this is your L, then B, L cross B. That means you are opening the screw. That means in upward direction. So your force will be in upward direction. And again here you see that is this conductor and B, it is making an angle of 90 degree. So this will be your force will be, here your force will be, that is I, L, B, because sine 90 is 0. So the magnitude of the force will be I, L, B. Now if you equate this I, L, B is equal to mg, then you can find out the value of magnetic field, that is I, L, B. So now you must have, so why I have selected this question? It is given in the book, it is a simple question. But remember that when there are this cross, that means when the formula is in cross product, it becomes a three-dimensional figure. So analysis of the force is the main factor. So here it is suspended in the mid-air by a uniform magnetic field. Uniform, this means it is suspended here by a uniform magnetic field. This is your uniform magnetic field. So to balance this weight, the force exerted by the magnetic field on this conductor must be upward. So the direction of the magnetic field must be into the plane of the paper. Then only this is L cross B. You are unscrewed. You are opening the screw. That means the force will be in upward direction. And if you can give all this direction, then this calculation is easy. You have to, all data are given here. You just place the data, you will get the answer. Now my next question, it is also from the textbook. I have taken from the textbook because these are simple questions, but yet they are very important to make your concept clear. Now my next question is here, it is from the textbook. Here you see the second question is, if the magnetic field is parallel to the positive y-axis, is parallel to positive axis, and the charged particles is moving along the positive axis, x-axis, which way would the horizontal force, the Lorentz force be A, an electron, and B, a proton. So here you see that if the magnetic field is parallel to the positive y-axis, if the magnetic field is parallel to the positive y-axis and the charged particle is moving along the positive x-axis, which way would the Lorentz force for an electron and for an proton? The most basic thing I want to tell you, which no one has ever told you. You have seen that if you take this y-axis as positive, then you should take this x-axis this side as positive, and here this is your z-axis as positive. But remember that if you take this x-axis here, x-axis as positive, and this z-axis here positive, then your y-axis will be in this direction, positive will be in this direction. If you are taking this x-axis along this direction, then your y-axis, positive y-axis will be along this direction, along this direction. You remember this. This is the very basic point. That means if you are taking y-axis along this direction, then your x-axis must be in this direction. This will be your positive direction, and that means originally when we draw in 2D plane, this is x and this is y. This is x and this is y. Now if you shift this y here, if you shift this y here, then your x will move here. Your x will move here. And if so, here if you are taking this x, so your y, this will be your positive. But if you are taking this y, then this x, this side will be your positive. This is a very basic point. So this is a very basic point. So now, since it has been clearly told that if the magnetic field is parallel to positive y-axis, that means parallel to positive y-axis, that means it is into the plane of the paper, it is moving into the plane of the paper, magnetic field, it is moving into the plane of the paper. Here you see, it is moving into the plane of the paper. That means this is the x-axis, and here this is your y-axis, and this is your z-axis. So here particles moving, the particle here it is moving in, here it is moving in x-axis, the particle is moving in x-axis. So what will be your Lorentz force? So Lorentz force, you know that it is Q, that is V cross V, V cross V. So here you see that for proton, V is along x-axis, that is I cap, and B is along y-axis, that is j cap. So I cap cross j cap, it will be k cap. So your Lorentz force will be in the positive, it will be in the positive z direction, in the positive z axis, in the positive z axis. And here, because the electron, it is negatively charged, so here your force will be in your negative z direction. It will be your negative z direction. So this is it is a very easy question, but the most basic thing here is that if you are considering x, these things no one has told you up till now. So I want to tell you, if you are considering this as the x-axis, then your y-axis will be positive in this direction, not in this direction. But if you consider this as y-axis, then your x-axis will be, the positive x-axis will be this direction. Now I am going to another question. All these are textbook, these are conceptual questions which are very easy question, but it carries a great concept. Your next question is consider a tightly wound 100-turn coil of radius 10 centimeter, carrying a current of 1 ampere. What is the magnitude of the magnitude of the magnetic field at the center of the coil? At the center of the coil. At the center of the coil. So see here, it's a very easy question. Only the thing I want to tell you, that do not confuse with this 100 turns coil and 100 turns coil and solenoid. Do not be confused with this 100-turn coil and solenoid. Because here this 100-turn coils, here your magnetic field at the center will be mu naught n I by 2r. This formula, your formula will be your B is equal to mu naught n I by 2r. If it is mentioned solenoid, then only your magnetic field at the center will be mu naught n I, where n is the number of turns per unit length. Remember this. So do not get confused that when it is told, in the question it is given here 100 turns coils. So coil, it is not a solenoid. So the magnetic field at the center will be this. We have to use this one. You do not confuse with this solenoid. Do not confuse with this solenoid. Now, my next question here is current carrying loop circular loop lies on a smooth horizontal plane, can a uniform magnetic field be set up, in such a manner that the loop turns around itself, around itself, that is turned about the vertical axis, about the vertical axis, about the vertical axis. A current carrying circular loop lies on a smooth horizontal. It is lying on this horizontal plane. Current carrying, this is horizontal, means in the XY plane. It is this is in the XY plane. So here you know that torque is equal to magnetic moment cross B, and your magnetic moment is IA cross B. This is your magnetic moment. Torque. So now here you see what happens. That means again see a 3-dimensional. The case becomes a 3-dimensional because we know that this area vector, its direction is perpendicular to the plane. That means it is perpendicular to the horizontal direction. So since area is perpendicular to the horizontal direction, the torque to create rotation, torque must be in the vertical direction. Remember, the torque must be in the vertical direction to rotate it. You have learned in class 10 that torque must be in the vertical direction to rotate a screw. So the torque must be in vertical direction to create a rotation. So now here that means rotation about the vertical axis. This is a vertical axis. So here the area vector has taken the vertical axis, the direction of the, because area vector has taken the vertical direction, because the area vector, it is lying on the horizontal plane, on the XY plane. So your area direction of area is along the Z axis. So it has taken the Z axis. So ultimately the torque will be in the XY plane. So your torque will be in the XY plane. Will be in the XY plane. XY plane. Torque will be in the XY plane. So since the torque is in the XY plane, so rotation in the vertical axis is impossible. So remember that you have learned in class 11 that the torque must be in the vertical direction to create a rotation in the along the vertical axis. But here the area has taken the vertical direction, and since this is the cross product, so all these three must be perpendicular to each other. So the torque will be in the direction of the will be in the XY plane, and so this can't rotate the loop in the along the vertical axis. So these are the basics which you must learn. These are the basics which you must learn. Then only you will find an interest in the subject, in this subject, in this chapter. So remember, you try to deal maximum problems where there is cross product, because the things goes into 3 dimensions and the directions are the basic factors. Then if you are clear with all this, you will be able to solve any type of questions. So this is for today.